Hello, and welcome to Lesson 33 of this Introduction to Calculus with Wolfram U. The topic for this lesson is exponential functions. So let's begin with a brief overview of the lesson. So in the past we've talked about polynomials and other kind of functions. So for example, over here, the function f is a polynomial function. The function g is a rational function. The function h is an algebraic function. And the function p is a trigonometric function. So here are the plots of these functions. And in this lesson, we'll go a step forward and talk about so-called exponential functions. So let's begin with a definition. So an exponential function is a function of the form a to the power x, where a is a non-negative number. And of course, what that means depends upon what x is. So if x is a positive integer, then all that you do is you multiply number a by itself x times. So here's 3 to the power 4, and that's just 81. But if x is a negative integer, then you take a reciprocal. So in this case, you have 3 to the power negative 4, giving you 1 over 81. And finally, if x is 0, then a to the power 0 is just 1. Of course, you can go beyond that. So if x is a fraction, like p over q, then you could either take a pth power and then a qth root, or the other way around. And in the Wolfram language, we have the surd function, which does that nicely for you. Now, the main point is that these exponential functions grow very fast. In fact, they grow faster than any polynomial function. So here are some plots of these functions. So if a is greater than 1, like 3 to the power x, then you have a very rapidly growing function. But if a is between 0 and 1, then the function is a decreasing function. And of course, if a is 1, then you only have a constant function. So increasing, decreasing, constant. Next point is there are several laws of exponents. So if you have a to the power x plus y, then that's the same as a to the x times a to the y. And if you have a difference, like a to the power x minus y, then you simply divide to get a to the power x over a to the power y. And if you have a to the power x to the power y, then you simply multiply the exponents and you get a to the power x times y, like over here. And finally, if you have a times b to the power x, that's the same as a to the x times b to the x, like over here. Okay, so now let's talk a little bit about some deeper properties. So first of all, the exponential function is always continuous, which means that there are no breaks in its graph. The domain of the function is all real numbers, and the range is from 0 to infinity. But of course, what happens to the function when you approach infinity depends upon the value of a. So if a is greater than 1, then as you approach infinity, you get an infinite value. As you approach negative infinity, you get 0. And just the opposite happens if you have a number a between 0 and 1. So now, when you approach infinity, you get a 0. When you approach negative infinity, you get an infinity. Okay, so on to the derivatives of these functions. So the point is that the derivative of a raised to x is not x times a raised to x minus 1, as you might think, but in fact it is a to the power x times logarithm of a. So here's the derivative from d. Now the question is, in which case does this logarithm term become 1? So that happens when the number a has got a special value called e, and this e is named in honor of the great Swiss mathematician Leonhard Euler. So if you solve log x equal to 1 with the solve function, you get back that x is actually e. So in the Wolfram language, we use e for the number, and we use x to represent the exponential function whose derivative is e raised to x. So the point is that this is the one function whose derivative is itself. So you just get back e raised to x when you try and differentiate it. And of course, you've got something more complicated like over here, then you can use the chain rule and get back the answer. How about integrals? Well, the integral of e raised to x is again e raised to x plus, of course, the c. But if you have a more general exponential function, a raised to x, then you get back a raised to x over logarithm of a. Okay, so let's just go a step deeper into the number e. So there are many ways to define e. The simplest one is, of course, to just say that e is a number for which the log of x is equal to 1. But you can also define it using limits. So this limit over here becomes 1 when x is e. And so does the other limit over here, which really is a sequence limit. N is a natural number. So when n becomes very large, then 1 plus 1 over n raised to power n becomes e. Also, the area under the curve 1 over x from 1 to a becomes 1 when a is the number e. And finally, you should know that the approximate value of e is about 2.71828. That's a very important approximation, well worth memorizing. And the number e is really, really important in mathematics, in science, engineering, and you will come across it all the time when you try and apply mathematics to practical situations. So, as examples of where it occurs, we can talk about exponential growth or decay. Now, for example, you've got bacteria, and initially there are 10 bacteria, and then they double every hour, then that's the law of growth. That's the initial number, that's the growth rate, and here's a plot showing that we actually have exponential growth in this case. But on the other hand, if you have radioactive material, then you begin with some quantity like over here, and the quantity, let's say, halves every time period, then you have radioactive decay. So there's growth and there's decay, and both of them can be modeled very nicely using exponential functions. So just to summarize, an exponential function is a function of the type a raised to power x. If a is greater than 1, it's increasing. If a is less than 1, it is decreasing. And of course, there are many laws of exponents which are useful in practice. Now, in general, the derivative and integral of an exponential function are constant multiples of the function. But the special number e has a property that e raised to x has got integral and derivative both equal to e raised to x, plus of course the constant c for the integral. And the number e is really useful in many different fields. For example, you can talk about exponential growth and decay, and you might want to use the number e or some other base for the exponential. So in the next lesson we'll talk about logarithmic functions, but before that, do revise today's lesson. It's an important lesson. Exponential functions occur all the time, and you should know them really well. So I'll stop over here. Thank you very much.